Well, it's time to begin study hall and our final exam review. We might as well get started because we have a lot to go over. I would advise that anyone listening prepare to take notes so you can jot down some things um, to remind you what you don't recognize, what you don't understand, what you don't remember, so you can go over it one more time in your review. Okay? Okay. Let me load up our presentation and we can just go to work. Okay. This is the final exam review for Earth Science A. And really, I put together this PowerPoint not to give you the answers to the final exam, not even to tell you what all the questions are. But what I want to do is I want to direct your attention to the important topics, things I know have been questioned about in past exams, so that you study those most commonly questioned items. Does that make sense? So that's what we're going to be doing. Okay, I'm just going to be doing some reminders. So as we go through this, you're going to find that the final exam uh, can be, well, successfully completed if you can do some things and if you know some things. So that's the kind of stuff I'm going to be reminding you of this evening. So let's get started. Let's talk about thinking like a scientist. Okay, thinking like a scientist. To think like a scientist, that means you solve problems by using a rather uniform and sequential pattern of steps. Okay? We always begin by, first of all, we have to figure out what the problem is, what a definition of the problem is, or identifying what it is we're really looking for. Okay? Once we figure out what our hang up is, we can then uh, gather enough information to possibly propose a possible answer or solution to that problem or question. And then we can take that possible answer or solution and we can test it to see what happens. We'll gather data about what's going on during our test. And then by analyzing that data, we can come to a conclusion. Did we support that possible answer or solution, or did we not? Okay, if we supported it, hey, hooray, that's good news. We can celebrate a little. But what about if we don't? What if we prove that it's wrong, or at least don't support it? Well, we can still celebrate because we have eliminated one possible answer, and that's success. So don't think of experimental failure as being failure. It's just a battle. You lost a battle. You haven't lost the war. So go back to your problem or your question and build a new possible answer or solution, and then go through the steps again. Okay, that's thinking like a scientist. The hypothesis I referred to is a possible answer to a question, and it has to be testable, folks. And we actually gave you a format for putting together a good hypothesis. The if-then format, remember that? A lot of you forgot it the minute we left that unit. But it's really valuable, and that's why I tried to hold you to it when you did lab reports. If I do this, then I predict this will happen. You see, that's your possible solution or your possible answer. Okay? That's where your if kind of introduces your independent variable, the thing you're going to test, the one thing you're going to change in the experiment to see what effect it has. The then part of your hypothesis is predicting what the resulting action will be, what your observable and measurable outcome may be. When we get done testing, sometimes we have a lot of these tests that have supported a hypothesis, in which case a hypothesis morphs into a theory. A theory can actually become a law, a scientific law. You see, if it has so much support and no proof against it, then we can actually use that hypothesis or theory to predict other events. I mean, let's face it, the law of gravity is accepted as a scientific law, right? And we predict stuff based on that all the time. What do you predict will happen if someone trips over a large rock while running in a race? You predict they'll fall? What do you predict will happen to a lead weight if you let go of it from a height? You think it'll fall and hit the ground? You see, those are predictions we're making because we have that much support in the law of gravity and that much faith in it that we can make predictions based on it. Okay. Here's some things that you need to know about. Can you define or explain what these things are? Earth science, geology, oceanography, climatology, meteorology, astronomy, environmental science. You need to be able, to talk about these things, make statements about them, describe them, define them. All right? And the Earth. Do you need to know the interior of the Earth? Yes, you do. You need to know the various layers, constituent layers of the Earth, from the outside all the way to the middle, and be able to talk about them, make descriptions of them, or use them to talk about things that go on in the Earth. Okay? We talked about mapping, didn't we? Do you remember mapping coordinates to find or to locations of places on the face of the Earth? Do you remember how that worked? You use latitudes in degrees and which direction, north or south of the equator, and longitude in degrees, maybe even in minutes and seconds if you want to get very precise, east or west of the prime meridian. Okay, and what do we use it for? Well, a couple of things. For example, if I asked you where the letter C is located, could you say 0 degrees latitude? Yeah, okay. And would you say 140 degrees west longitude? Okay, so you know how to do that. Okay. But what if I said, if I gave you a coordinate like 40 degrees north latitude, 40 degrees west longitude, could you find that? It's not one of the lettered points, by the way. Have you found it? If you have, you know you better doggone well be on a boat when you get there because it's right there, folks. Look where the finger pointer is. 40 north, 40 west. Okay? So there's a couple things we can do with coordinates, but it's all about following lines of latitude and longitude and where they intersect. Okay. Can you read maps? We spent some time reading topographic maps. Do you remember what they're like? Well, if you don't remember how to read a topographic map, you need to go back and brush up on that. There will be questions on reading a topographic map. There always are. Okay. So what do they tell you? Well, they place all kinds of natural and man-made features on a map, and that map also gives elevation. So you see lots of lines on it. Those lines are contour lines that connect points of equal elevation. Okay? And every so often, one of those lines has a number on it. It's called an index contour. And if you know the contour interval, that's the distance between contour lines, you can figure out what the unmarked ones are as well by simply starting from one of those index contours and going this many, this many, this many for each line. Okay? There are other things that can help you with those elevations because they often put numbers not only on the contour lines, but also on some of the high peaks as well as the low depressions. And remember, just at first glance, if the lines are close together, it's a steep slope. That means there's more vertical change, height, altitude, elevation, than there is um, horizontal change. So close lines, steep. Lines far apart, it's a lot flatter. So if you don't remember topographic maps, you may want to bone up on that. Are they the only kinds of things that are mapped? Elevation? No, no, no. Certainly not. I mean, all of you have seen highway maps, right? In the gazetteers or in a road atlas, or even an old-fashioned highway map folded up in the glove compartment of your grandpa's car. You can also map soils. You can map temperature patterns. You can map where rock formations are found. There's all kinds of things that man has put on maps to help him with various tasks. Okay? Okay. How about water? Can you map water? Yeah, it's kind of the opposite because in water, the contour lines are going to represent uh, the same thing. They will represent points of equal, but it'll be depth instead of elevation. Okay? So you're measuring down, but you're still measuring vertical distance. When you got into the study of rocks and minerals, did you figure out what a rock was by definition or a mineral? Did you figure out how they're related? Or do you think they're the same? Hint, 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 they're not the same, but they are related. Did you learn anything about how to test and identify rocks and minerals? Hopefully you did. Hopefully you still remember things like uh, color and hardness and streak, all of those kinds of characteristic tests that help us identify the minerals found in certain rocks. Okay? Okay. And how would you tell if something were a mineral? Would you go by the identification tests, or would you be real smart and refer back to the definition of a mineral and see if this particular uh, key substance fit mineral characteristics? You know, is it inorganic? Is it a solid? Is it, and so on, okay? When talking about rocks, you have to know the rock cycle because it is the relationship between all rock on the earth, whether they're on the surface or below the surface. All rock is related because all rock comes from previous rock. Okay? Igneous rock forms when molten rock, magma, or lava cools and crystallizes. Okay? Now, if an igneous rock should break down by weathering and the resulting sediments are transported by erosion, and then by deposition they become a sediment layer, we find that those, when buried, may develop into sedimentary rock. Okay? Yeah. As they're buried, they're subjected to heat and pressure of the layers above them and the actions of certain types of fluids to uh, compact them and cement them together. Now, further heat and pressure at a depth in the crust can change the form of some rocks, making them into metamorphic. And of course, metamorphics may eventually be heated enough to melt, in which case they may develop into new igneous rocks. Now, that's just one look at the cycle, okay? But the thing you need to remember about the rock cycle is anything can happen. The shortcuts can occur, okay? So an igneous rock can be changed to a metamorphic rock with enough heat and pressure at depth. Okay, an igneous rock can be remelted and then recooled and crystallized into a new igneous rock. Okay, and actually, an igneous rock, if uplifted to the surface and subjected to the proper agents of weathering, can be weathered into new sediments. And then what? Uh-huh. Yeah, we're talking a new kind of rock now, sedimentary rock. But you know, igneous rock, sedimentary rock, metamorphic rock, they can all be weathered and eroded to produce sediments which can later be lithified into sedimentary rock. Igneous rock, sedimentary rock, and metamorphic rock can all be superheated and melted. And lo and behold, with cooling and crystallization, become igneous rock again. All of them can. And what's really interesting is that metamorphic rock, that rock that is formed by massive heat and pressure below the surface, uh, it can actually be changed too into a new form of metamorphic rock. Or if it's uplifted to the surface and subjected to the proper agents of weathering, it can be weathered into sediments and form sedimentary rock eventually. Or it can be melted and develop into new igneous rock. So as you can see, any kind of rock, when subjected to the proper uh, conditions, can be changed into any other kind of rock, including a new form of itself. That I find really interesting. Let's spend a little time with each of these groups that we find in the rock cycle. Okay, let's start out with igneous rock. Igneous rock, as we said, comes from uh, molten rock. Below the surface, that would be magma, and it would cool and crystallize into intrusive igneous rock. But if it finds its way onto the surface, magma then is called lava. And lava can also cool into what we call extrusive igneous rock. Usually, most igneous rock formation is associated in some way with volcanism. And as you learned earlier, the most common places for volcanism would be at the boundaries of crustal plates, like the Pacific Ring of Fire, which runs around the Pacific plate. Okay. Now, there are a lot of different types of intrusive igneous formations, and they all depend on their size, shape, how they were formed. As you can see, um, a neck is exactly that. It was a neck that protruded upward, and when, for example, it results in the formation of a cone. Maybe that cone might weather and erode away, leaving the hardened neck standing upright, like Shiprock, New Mexico. That's all it is. It's the remnant of a neck. It used to be surrounded by some kind of volcanic cone. You also have dikes and laccoliths. Dikes are a little smaller than laccoliths. A dike is usually a horizontal formation that forms like a dam or a dike. It might intrude between layers of rock and not reaching the surface, cool and hot in place. It's a little bit bigger. It would be called a lake of rock, or in Latin, that is laccolith. And that's how a laccolith got its name. It's a pretty large impoundment of magma, but in comparison to a batholith, which is a sea of rock, it's only a lake. Okay? And the smallest form of the horizontal intrusions is the sill. It's usually just that. It's like a windowsill. It's not real thick, real high. Now, a dike can extrude upward into cracks. So dikes can be vertical as well as horizontal. But you need to understand that the biggest of all of them would be the batholith. In fact, the core of the Idaho Rocky Mountains is a gigantic granitic batholith called the Idaho batholith. How about that? We have our own batholith. Pretty cool, huh? There are different kinds of cones. They're formed from different kinds of volcanic eruptions. If you just get a crack or a fissure in the surface and lava pours out on the surface in like a large fan out, not all that thick, but it runs out over the surface and covers a lot of surface area with a layer. That's usually called a fissure flow, because that crack is called a fissure. Okay, the Snake River Plain, the Columbia Plateau of central and eastern Washington were formed by fissure flows. In the Hawaiian Islands, you have these types of volcanoes that are not extremely high when compared to their width. So they're not all that steep, really. Now, don't get me wrong. You try to climb up the side of one, yeah, you may be out of breath. It be extremely difficult because they are steep. But it can be several thousand feet high and many miles wide. So comparing its verticality to its horizontal position, my goodness, no comparison. And they're formed when you get a very thin lava. It's not viscous at all. And so before it has a chance to cool, it flows and runs out great distances, hence the flatness of those cones. Okay? Okay. Another type is ash or cinder cone. And that's usually from uh, explosions that pulverize a lot of rock, and so they send out a lot of cinder, rock, small rock, and dust. And so the cone around it is rather steep. Now, it may not be huge, but it's steep because it is usually more vertical than horizontal, and you get a lot of ash sliding down its sides. Okay, the buttes in Butte County, Idaho, the cones over by Bend, Oregon, are all cinder cones. We also have a rather combination type cone. It's built up from alternating explosions that spread ash and cinder and particulates. And then the next time, maybe it would be uh, a fluid or even a viscous lava. And so you get layers. We call that a stratovolcano because it has strata, layers. Sometimes it's called a composite volcano. You find both terms used in geology. And then they would make up rather large mountains. Most of the major mountain peaks in the Cascade and Sierra Nevadas are composite cones. Mount St. Helens, Mount Rainier, Mount Hood, Mount Shasta, Mount, all of those. And it's the same all the way up through British Columbia to Alaska. Lots of composite cones. Denali is a composite cone. Now, every now and then, a cone forms and the magma chamber below it, through massive and violent eruption, empties itself. And so you have this massive cone sitting above an almost empty magma chamber, and the top of the cone collapses down into that chamber. Now, that gives you a shorter volcano or volcanic uh, um, cone, but it's also wider at the top, isn't it? Take a look at this caldera volcano in the lower right. Yeah, that's called a caldera. Crater Lake is not in a crater. It more accurately should be called Caldera Lake. And the island, Wizard Island, out in the middle of the lake, that's another attempt at eruption. That's a tiny little cone that has formed from the bottom of the caldera. See, this stuff can be really interesting if you get into it. So I hope those of you who find this stuff interesting, find yourself a geology course either in high school or college and get into it a little bit greater detail. Now, when you think of a volcano, what do you think of about its danger? You think of, oh, it's going to explode like Mount St. Helens did. Or you think of like Kilauea on the big island of Hawaii. Oh, it's going to cover everything and in lava. But there's more danger than just those two items. For example, sometimes the eruption cloud can, if it's a huge enough uh, explosion, like Krakatoa was in the 1880s, it can send a gigantic cloud of smoke and dust and particulates into the atmosphere that can circle the Earth, and it can happen for months, even years, leading to a little cooling of the surface. That can be dangerous. And what about if that cloud has poisonous gases in it and produces acid rain? That's dangerous. What about if the eruption creates a landslide? Or it blows out a lot of rock and particulates, and you get what is called a pyroclastic flow, which is a mixture of rock, cinder, ash, heat, poisonous gas that can travel down the side of a mountain at 60 miles an hour. That's not cool either. And what about if this is a mountain that had snow or glaciers on it? Where's that meltwater going to go? Well, where did the meltwater go when Mount St. Helens erupted? It created a mud flow or a lahar that went for many, many miles. Yeah, it flooded the Toutle River, uh, wiped out homes, bridges. So my point is there's more than one kind of danger from volcanic eruptions. So you need to be familiar with what these dangers are. Okay? Um, let's talk a little bit about metamorphic rock now. Metamorphic rock. That's the type of rock that is changed due to tremendous heat and pressure over time. And often the question is how much pressure, how much heat. It varies. It really does. But I can tell you this, both are tremendous. Okay? And what happens is if this tremendous heat and pressure is built up from tectonic plate movements, it can affect an entire region or portion of a continent. That's called regional metamorphism. But there is another type of metamorphism called contact metamorphism, and it's more limited in the area it affects. It only affects a ring around a magma chamber. The heat of that magma chamber plus the pressure of being at that depth combines to change that halo of rock around the magma chamber into a new kind of metamorphic rock. Okay, that's contact metamorphism. It's in contact with a magma chamber and has great pressure from being at depth. All right? There really isn't a lot we can say about metamorphic rock. The part that surprises a lot of people is that one kind of metamorphic rock can become another kind. Yeah, see what your textbook says about shale, slate, gneiss, and schist. What kind of rocks are they? Okay, let us move on. Now we're going to talk a little bit about one of our old friends, sedimentary rock. Sedimentary rock is so named because it is formed from weathered and eroded sediments that have been deposited in horizontal layers. Oh, the principle of horizontality. If you're not familiar with the laws of uh, sedimentary rock and aging and dating fossils, you might want to review that as well. Okay. Now, how do we recognize sedimentary rock? Those horizontal layers. They'll have strata, and sometimes they'll have other oddities in layers like mud cracks and ripple marks, and of course, fossils. Sedimentary rock is the only kind of rock that will have fossils in it. You see, the heats and pressures involved with forming igneous rock and metamorphic rock destroy fossil remnants. What is a fossil? Well, it's any remnant of a living organism, plant or animal, even bacteria. We've found bacterial fossils. Yeah, Google it. Yeah, it's interesting. But they are quickly covered and preserved before they can, decay away to nothing, or before they can be destroyed by uh, uh, predators and other prowlers, uh, things that live off of dead plants and animals. So this quick burial is really essential in the formation of fossils within sedimentary rock. So, in summary, this is how all the types of rocks are formed. Each type of rock, subjected to the proper events and forces, can become any other kind of rock. Keep that in mind. Okay, that's an important concept about the rock cycle. Now, moving on into more about rocks and minerals, can you define these terms? Remember, we had a little bit about geochemistry, the chemistry of rocks and minerals. And so we reviewed some of the basic concepts of chemistry. You need to know these things about chemistry, okay? Yeah, there are usually questions about them. Is there a question about every one of these terms? No, probably not. But you don't know which ones. So you have to be familiar with all of them. So as long as we're talking about minerals, let's talk about identifying minerals. You did a really interesting lab on that, an interactive lab that most of you did quite well on. And it was all about identifying minerals. Whoops, there we go. Now remember, if we want to know if something is a mineral, we don't use these. No, we use the definition of a mineral and see if that hard piece of rock fits those characteristics. When we determine that it's probably a mineral, that's when we go to these things to try to identify which mineral it is. What's its hardness? 1 to 10 on the Mohs scale. What scratches what? And we have some basic tools like copper penny, a steel nail, or an iron nail, our fingernail. They have known hardnesses that we use as reference points. Color, there's another one. Now, most people think color is the best one to use. No, it's really unreliable. One thing, there's several different minerals that are the same color. Yeah, so it wouldn't differentiate between them. And we have found that there's a different color sometimes between wet and dry samples. So when we're talking color, let's always talk about a dry sample, okay? Streak has to do with the color of the crumbles as you forcefully drag your mineral across a porcelain surface. It is going to break down usually into crumbles and leave a trail or a streak of colored crumbles. that color isn't always the same as the color of the rock. Yeah, see? We also use luster, which basically describes the surface shine, or in some cases, the lack of shine. Cleavage and fracture refers to how it breaks. Uh, we sometimes talk about specific gravity, which is very similar to density. It's calculated the same way. That is, mass divided by volume. And there are special properties that help us with certain minerals because some of them, the iron bearing ones, for example, are magnetic. Magnetite is magnetic. Others can be attracted to a magnet if they have iron in them. Phosphorescence, how they glow. Luminescence, radioactivity, chatoyancy. Okay, so those are kind of like bonus characteristics. If you run into one that has these things, it really narrows down the possibilities quickly. So it's really nice when you find one that has special properties. Okay, what are rocks for? One of the things we use rocks for is we have used them to establish what we call geologic time, a scale of time that sets out what the Earth has been like as it has aged since its formation. And there's a couple different ways we measure geologic time. One is called relative dating, and that's basically just comparative dating. You know, if you found things at different comparative depths, one thing at a depth of 600 feet and another one at a depth of 100 feet, you would assume that the one at 600 feet is probably older. It was laid down before the one at 100 feet, right? So that's what relative dating is. It's how old things are relative to another. Okay, now the more reliable method is called absolute dating. Sometimes it's called uh, uh, numerical dating, and sometimes it's even called radiometric dating because it uses radioactivity in its process. You see, absolute dating gives us a calculated age of radioactive substances compared to their normal isotopes. Let me give you an example. Carbon-14 has a half-life of 5,730 years, which means that every 5,730 years, half of that carbon-14 will remain and half of it will have changed to carbon-12, a stable form. Okay? So, if we find something that has just 1/4 of it is the radioactive elements, then we know it has gone half once and half twice, right? Yeah, to get to 1/4, it's had to have been cut in half twice. So we've experienced two half-lives. One half-life is 5,730 years, so two half-lives is 11,460 years. So we would calculate the radiometric dating age to be approximately 11,460 years. Cool, huh? Now, not everything has the same half-life. Some things half-lives are in hundreds of thousands of years, some in millions. That we have even found substances that have a half-life of over 1 billion years. Yeah. And then there are some who their half-life is 2 seconds or a week or a month. So as you can see, there's a wide variety. But the one thing we can bank on that we have discovered is that the half-life of a uh, radioactive isotope never changes. It doesn't matter how long it's been decaying in the earth, its half-life is still the same. It doesn't matter if there's a ton of it or a pound of it, the half-life is still the same. It doesn't matter if it's found in Africa or South America, the half-life is still the same. Half-life of a radioactive isotope of an element is a characteristic of that isotope. Okay? Okay, so what we have learned from these two things, the relative dating and the absolute dating, is that the Earth was formed approximately 4.6 billion years ago. And we have divided the time of the Earth into 4 eons: the Hadean, the Archean, the Proterozoic, and the Phanerozoic. And then what we've done is we have divided down these eons into numerous eras. And we've subdivided the eras into periods, and many of the periods have even been subdivided into epochs. Okay, so these are all based on what was going on the earth during that time span. You know, what kind of life existed, or did life exist? You know, what was the dominant life form at that time frame? And so, you know, each one of these subdivisions has a more and more and more specific uh, um, fossil type that we would associate it with. Okay? So let's have 1,000 atoms of a radioactive isotope in my rock. Okay? It has a half-life of 2.5 years. How many atoms are going to remain after years? Okay, here's a couple questions for you. Do you know what the principles are that are involved with relative dating? Do you remember any of them? Not 10 minutes ago, I mentioned the law of, or the principle of superposition and of, yeah, that's a hint. Okay, so first of all, do you know any of those principles? Second of all, how many atoms remain? Well, let's just take a look, okay? Let's see if you got it right. Do you remember the principle of superposition? That is, the lower down you are, the lower you are in the layers. The principle of original horizontality, which says that uh, unless exceptional conditions exist, each layer has been laid down horizontally or deposited as horizontal sediments. Cross-cutting relationships. Any formation that cuts across other formations is younger than those that it cuts across. That goes for uh, any kind of fault line, for example. And the principle of inclusion. If something is included in rock structure, it existed before the formation of that rock structure, so it's a little older. Okay, how about the half-life thing? In 10 years, it'll have gone through 2.5, 2.5, 2.5, 2.5, 4 half-lives, right? Is everyone with me on that? Okay, because 2.5 goes into 10 4 times. All right. Now, what happens each of those four half-lives? Well, after the first half-life, you got 500 and 500. Half of them have turned, right? After the second half-life, half of those 500 turn. You now only have 250. After the third half-life, half of those 250 have turned. You now have 125. And so at the fourth half-life, you only have half of that 125, which is approximately 62 and a half, with 937 and a half new daughter atoms. Only 62 and a half radioactive parent atoms. Does that make sense to everyone? I hope so, because you may have to make one of these calculations on your exam. Here's an example of the geologic column and some, not all, just some of the uh, subdivisions. As you can see, Precambrian time basically makes up the first three eons. After the Proterozoic eon, we start the Phanerozoic. And the very first thing in the Phanerozoic era is the Cambrian period of the Paleozoic era. You see how I got that? And you can see that's when the first appreciable multicellular life forms began. This is the very first evidence we have of life forms. And so the types of life forms you see are what we call the dominant life form of each of those. So look at the Silurian. You see fishes and sea life. Can you see that? Yeah. How about the Carboniferous? Yeah, you can see there's a tropical forests and insects. Hey, look at this. Now we're seeing something interesting. As we get into the Mesozoic era, it looks like there's a dominant life form that entire era. Can you see it? It's the age of reptiles. Yeah, various kinds of, need I say it, dinosaurs. Now, when the dinosaurs disappear, we get a new dominant life form on the earth, and it's mammals. And so the Cenozoic we've often referred to as the age of mammals, as opposed to the age of reptiles, as opposed to the age of fishes, as we have seen. And if you look up towards the top of the Quaternary period, you see a new dominant organism. Recognize him? Yeah, it's George of the Jungle. Well, I don't know what it is, but um, it's basically man has become the dominant mammal. Okay. On the right is just an example I put up to show you how half-lives occur and the numbers change. You know, you go from 1,000 as the example that we were looking at earlier to 500 to 250 to 125 to 62 and a half. You know, each one of these half-lives, regardless of the number of years involved, cuts the number in half. And of course, the opposite is occurring with the new daughter atoms that are stable and don't break down any longer. Yeah, you go from 0 to 500 there as well. Yeah, instead of going 1,000 to 500 as the parent uh, atoms did. You go from 0 to 500, and then it continues to rise and rise and rise. So the two numbers are opposite but equal, aren't they? Interesting. Now, lately, we've gotten into a study of plate tectonics. This should be more familiar to you. As you recall, we started with a discussion of Wegener's theory of continental drift, Pangea breaking up, drifting apart. But his theory died off because he couldn't offer a mechanism for this movement. Why did they move apart? See, he could prove that they moved apart. He had plenty of evidence for that, but he had no evidence to tell why. Well, later on, we discovered seafloor spreading as scientists during World War II and into the 50s and 60s began exploring undersea phenomena, the seafloor and the mountains and the valleys found at the seafloor. And we began to learn more and more and more. And part of what it came out of it was this idea called seafloor spreading, where you have divergent plates move apart and new magma welling up onto the surface, producing new sea bottom, sea floor at what we call mid-ocean ridges. And this all happens because of convection cells in the mantle. And so these convection cells lend themselves to slab pull, ridge push, and from the convection cells. Okay? Okay, so let's just look at that. Since the seafloor spreading, the idea that Harry Hess developed, since it is going to offer us a new mechanism for the plates moving, let's take a look at it real closely. And you can see that warmer magma moves upward. Why? Why does it move upward? That's right, because being warmer, it's less dense. So what is that going to do for the cooling magma? Right, it's going to become more dense, and eventually it will settle back down to be warmed again. That is the key to the convection cell. Then, as this rising magma reaches the surface to where there are two diverging plate boundaries, it pushes its way through between them, forming mid-ocean ridges, and that is the concept that we are familiar with, ridge push. Okay? Yeah, it's pushing those plates apart. Then, as some of that magma that doesn't escape and push the plates apart, as it is deflected aside, it tends to drag on that plate, giving a secondary pull. And then thirdly, as that moving plate collides with other plates, it is often subducted down, which gives us a little bit of slab pull as well. Okay? But between that ridge push and slab pull, it's moving these continents apart, exactly like Alfred Wegener had stated. We now have a mechanism. And we now have a new concept. We have a concept called plate tectonics. Now, once again, here's a review of Wegener's reasons for continental drift. I mean, things like similar rock and mountain structures that are found on opposite sides of oceans, uh, plant and animal fossils found on opposite sides of oceans, great distances apart, um, various kinds of deposits. Well, before I get into that, I think yeah, just real quickly, I want you to look at this. This is basically a dramatization of what happened uh, for, 225 million years. Continents broke apart, moved to new positions, and they continue to move today. So how come we can't see it? We're talking millions of years, remember? Yeah, and we've only had maps of the Earth for maybe 600 years, and they weren't that great. And we've only had photographs that have occurred in the last 100 years, less than that actually. So anyway, um, what was I saying? Doggone it, I lost my train of thought. Oh yeah, things that were evidence to him. Um, Finding evidence of different climates, you know, showing that portions of South America were near the pole, or that uh, Siberia once was in a tropical climate. Things like that. Okay. Anyway, speaking of plate tectonics, it basically says that the crust of the earth is broken up into many different plates, and with the movement of the mantle below them, they are constantly shifting or in movement. For long, long, long periods of time, they move in the same direction. Does that mean they always have moved in the same direction they're moving today? No, not necessarily. But it makes for some interesting things, because the directions the plates move in reference to one another does a lot for what's going on the surface of the earth. Let's take a look at that, okay? There are three basic types of plate boundaries. As you recall, there are divergent boundaries where they are moving apart, convergent boundaries where they are moving together and colliding, and transform fault boundaries where they are moving in opposite directions, but not toward each other, but rather by each other. Okay? And we also have learned that convergent boundaries can be collisional, where they are very heavy and just plain collide with one another, creating great wrinkles that we know as major mountain ranges. Uh, or they collide, and one may be less dense than the other or thinner than the other, and it is forced down and under the other one, where through great friction and depth, it begins to melt away. And the formation of all that excess magma creates low pressure, so that magma is working its way towards the surface because it's hot and less dense, and it's rising, trying to find cracks, crevices, anything it can to rise, creating volcanism on the surface. Also, if, as I said earlier, new seafloor is being produced at divergent boundaries, it is being melted and recycled at these convergent boundaries. That sure helps, doesn't it? Yeah, because I know When I first learned about the making of new seafloor, my first question was, well, how come the Earth isn't swelling then as we get more and more and more continental mass like that, or seafloor mass? Now you know why. There's a little bit of recycling going on. Mother Nature thought of recycling long before man did. So in plate tectonics, we get this seafloor spreading at divergent boundaries, creating new plate, and we get subduction at some convergent boundaries that recycles old plate. Yay! Great concept. Answers a lot of questions. And here I'm glad I went through and this over before I went through it with you tonight. I discovered an error, and I don't know how long this error has been in this presentation. I've had this presentation for 4 or 5 years, but I've changed it, okay? So I've corrected my mistake. Plate tectonics, okay? Convergent continental plate collisions can cause wrinkles known as mountain ranges. One of the biggest is when the Indian plate collided with the Asian plate. You get the formation and the continuing formation. Yes, they're still growing today. The Himalayas, the world's highest mountain range, and they're getting higher as we speak. Not quickly. I mean, don't take a trip to the Himalayas and sit there with your binoculars to watch the mountains grow. Okay? I mean, you think it's slow watching paint dry? Yeah, just sit and watch the Himalayas grow. And transform is like the sideways movement of the San Andreas Fault of Southern California, and it causes earthquakes and wrinkles. And of course, those wrinkles can get pretty big sometimes. I guess wrinkles isn't the greatest term in the world. Okay, let's look at earthquakes. A little bit about earthquakes, since we mentioned that movements can create problems. Well, what it creates is vibrations in the Earth's crust. That's an earthquake. Yeah, any movement at any boundary or any fracture or crack in the Earth's crust can create vibrations. And you and I feel them as earthquakes. So again, maybe we're using the wrong word. Maybe vibration, that's what they are, but they're so massive. Yeah, you know what kind of damage earthquakes can equate. Okay, so anyway, movement at crustal fractures or plate boundaries cause vibrations passing through the Earth's rock. Primary waves are faster than secondary waves because of the type of movement. They are a compression and release wave rather than a fluctuating vertical wave. So we can use that fact of their speed to determine distance. And then 3 distances can be used to triangulate an epicenter. It works like this. You're going to get primary waves sent out in all directions from this movement. Okay? Now, sometime after that, it could be a second or two, it could be longer than that, but there'll be a small lag in time before secondary waves arrive and can be measured on a seismograph. Okay? So by looking at the seismogram, we can look at how long between the arrival of the P wave and the S wave. That gives us a time in seconds. That time can be mathematically converted, and we don't have to do the calculations. We have charts and graphs, and we have computer things that can do these calculations for us in a moment. Well, anyway, this lag time gives us a distance, gives us a time and a calculated distance. So we draw a circle around that recording station with a radius of the distance that we just determined. And two other stations at different distances from the earthquake will also record the arrival of P and S waves. And because the distance is different, the time will be different. So because of that different time, they will calculate a different distance. They will draw a circle around that recording station with that particular radius, as they will do at a third station. Now, if you have one circle from one station, you get thousands of points around it, don't you? Look at the diagram. Look at the green circle around Minneapolis, Minnesota. Thousands of points at which that earthquake could have occurred. Now, if you add a second station, like the one in Detroit, what happens? Well, those two circles intersect in two places. We just cut the possibilities from thousands to two. But which one is it? By introducing a third station and its calculations and its circle, the three of them come together in one and 1 point only. That is the epicenter, the point on the surface of the earth directly above the movement or the focus of that earthquake. Wow. Cool. Now, all this crustal movement, I mean, plates grinding against one another, pulling away from one another, colliding with one another. I mean, it creates a lot of different stresses on the rest of the crust. Okay? And so with stress, you get strain. Do you know what strain is? Strain is just the result of stress. That is a change in structure due to the addition of stress. Look at this example. You can see that if you happen to push two things together, they compress. That's one type of stress. If you go to pull at opposite ends of something, like a crustal plate or anything else, you get tension or tensile stress. And if you twist them at angles, apply pressure at angles, that's called shear stress. Well, they can cause several things, several types of deformation. It can cause breaks and movements on opposite sides of the break. It can cause bending. I mean, bending is going to occur first. We saw that in one of the labs you do. Under pressure, we can get, like layers of cookie dough to bend, right? And the warmer they are, and the more pressure, we also learned that they bend more readily rather than break. But there is, a limit to how far things will bend, including rock. We can get rock to bend, to deform, but eventually it's going to break too. Well, talk a little bit more about that. The results from stresses built up by movement of crustal plates changes the shape and the volume of crustal rock by, first of all, bending it and then possibly breaking it. You see, you get three kinds of changes. One is called elastic change, where it bends and bends, and if you release the pressure, it will go back to its original shape. There's also what we call plastic change, where it bends and bends and bends, and eventually a release of the stress doesn't result in its resuming its former shape. It stays in this new shape. And then you have, of course, in less flexible things, a thing called brittle change. You know what that means. If something's brittle and you apply pressure to it, what happens? Yeah, it breaks. It may bend first, but it breaks. It shatters. So this gives us a lot of different types of crustal deformations. Because remember, the Earth's crust is under great stress from all this pushing and pulling. So you get faults, various kinds of slips, like a normal fault due to tensional stress. Very simply, the hanging wall will slide downward in relationship to the footwall. But in a similar break, if it's compressed rather than pulled, you get a reverse fault where the hanging wall will slide up and even over the footwall. And of course, those we call dip slip faults. Yeah, they dip when they slip. Okay? But there's a different kind too. It's called a strike slip. And that movement moves along in the direction of the fault. Okay? That's called a strike slip because the crack on the surface, the direction it runs is called the strike of the fault. And if it slips in that direction, sure, it's a strike slip fault. Okay? By the way, a normal fault or a reverse fault can become a thrust fault if one part is pushed up and over the other one. Oh, here's an interesting one here. This was first defined by German geologists when they said, well, what if we get almost parallel faults? And, you know, I can imagine, I can even see that under tensional stress, one might drop down between two others. Well, that's this set of formations. The high one, whether it rises or remains the same as the other one drops lower, is called a horst. Okay, that's kind of like a ridge. And the one that drops down, the formation gives you kind of a valley-like thing. That's called a graben. So horsts and grabens occur together because they're the result of parallel faults. I always remember this because if you were to sit on a horst, your legs would angle down both sides like you're riding a horse. Or you can look at it the other way. What does a graben look like? If you had just dug that little hole out, it kind of resembles a grave, doesn't it? Grave, graben. Yeah, I know. I have some pretty colorful memory keys, don't I? But these are the things that I mentioned to you because they're the things that have helped me remember terminology through the years. In faults, we have descriptions for the various kinds of faults. You know, if it's an upward fold, we call it an anticline. If it's a downward bend, we call it a syncline. Now, how are you going to tell the difference between a syncline and an anticline? Well, remember it this way. Downfold is like it sinks, a syncline. Make sense? Downfold, sink, syncline. And what's the opposite of something? The anti, right? Yeah, the anti. So a syncline goes down, so what are we going to call the one that goes up? The fold that goes up is an anticline. Memory keys, extremely valuable. What if there's only one bend? Yeah, you don't, it's not a full anticline or syncline. It's a little of both with one fold. Well, that's easy. What's a good word for one? Mono? Yeah, let's call it a monocline. We might as well, because that's what every other geologist calls it, a monocline, one fold, one limb. Okay. What about if we get a fold that's not horizontal? I mean, it actually is up at one end and then it sinks down at the other end, like it plunges. Yeah, well, it's an upfold, so it's an anticline. What kind of anticline? A plunging anticline, because it has an angle of plunge. Make sense? Yeah, that's the way they taught it, but I'm just telling you how to remember it. And there are a lot of different types of folds. Symmetrical ones where they look two in a row look the same, or they can be asymmetrical where they look different. The ones I like are, a symmetrical fold. If it gets pressured from the side, it can become asymmetrical. If it gets pressured some more, it can become an overturned fold, and maybe even become eventually a recumbent fold. A recumbent fold is basically it's just laying down. It's a fold that has been forced over until it's laying down. Like a recumbent bike. Have you ever ridden a recumbent bike where you lay down and the pedals are actually in front and above your eyes? Yeah, recumbent bike, recumbent fold. And how are folding and faulting related? Well, sometimes the fold results in a fault. So it is not uncommon to find them occurring together. For example, we get a start of a fold and we get some brittle layers that actually crack, giving us a fault line. We get some normal faulting, downward motion, which bends the upper layers. So you get a monocline above that normal fault. Makes sense? And it's all because the lower layers were brittle and broke, whereas the upper layers were more ductile and were able to bend. We finished up our discussions by talking about resources. And we didn't do a complete discussion of resources, unfortunately, but we did center on energy resources and went into them pretty heavily. Okay. Now, what we need to know about energy and our natural resources is that initial energy sources on Earth are very few, actually. They include the sun, internal heat, and the convection currents. Those are all left over from the formation of the Earth, and the force of gravity. That's it. Everything else evolved from that. Yeah, if you think about it. Nuclear fission is one that we didn't get to spend a lot of time on, but it derives its energy from the splitting of atoms. Or the other form of nuclear energy, fusion of atomic nuclei, which would be nuclear fusion. Of course, we have a lot of other very usable energy resources on Earth: fossil fuels, biomass, geothermal, wind, hydroelectric. Okay, especially important in the Northwest would be hydroelectric. Okay, yeah, because the Northwest's hydroelectric dams supply 11% of our nation's electricity. And most of what you and I use every day here in the Northwest is from hydroelectric. So when you wrote your essay on if your family could live on uh, alternative energy resources, hey, guess what? Hydroelectric is classified as a uh, alternative. So we stand a better chance of surviving on uh, alternative resources than many other places in the world, even the other places in the U.S. 3/4 of our energy consumption is fossil fuels, but the supply of fossil fuels is on the wane. And no time like the beginning, because as we have learned, the burning of fossil fuels produce greenhouse gases, right? Our oil reserves are estimated to last only another 20 years, which is the reason my wife gives for not wanting to buy a new car. She's going to keep her old car till she dies. We figure we've got 20 years left. Coal reserves, that's carbonized plant remains mostly, 200 years. But look how dirty coal is when it's burned for energy. Yeah, we're going to be using it after we should, to be honest. So conservation has been very important for energy resources and other resources as well. That's conserving it, using it wisely. Okay? Because remember, their use, that is fossil fuels, may contribute to global warming. Now, I'm not going to get in an argument with you. I did change the word to may, but that's just so that none of you would start arguing with me. I'm just not going to argue about it. Can you define these terms? Yeah, you need to know what they mean. And you need to know that preservation and conservation are not the same thing. So what's the difference? And how are they similar? What's the definition of mining? Is metal the only thing we mine? Can you mine water? Hmm. What's an alternative energy source? How is it related to renewable and non-renewable resources? What is fracking? Is that a good thing or a bad thing? It goes on in North Dakota and Montana, and they argue about it all the time. Okay, so I've given you a lot of hints. I want to give you one final piece of advice. Okay, in preparation for your final exam. Okay, um, I really recommend that you go back and look over your old tests and quizzes, even the reading checks. You may have noticed, or you may not have noticed, but the questions for the reading checks, the quizzes, and the unit tests all come from the same quiz bank. And they're all coming from the same quiz bank that your final exam is coming from, which means it is very likely that you will see familiar questions. You may see some new ones you haven't seen before, but you're going to see a lot of familiar ones. By going back and looking at your old reading checks, quizzes, and tests, you can find out which ones you missed and you can figure out what the right answer is in case you face that question again. That's just common sense, isn't it? And if you took notes on anything, go back and check your notes. Now, I know I asked you to keep a notebook, take notes on your readings and the videos, but I know most of you didn't. I'm not a fool. I was not born yesterday. Believe me, I was born many, many yesterdays ago. But if anyone did take notes, review your notes. Okay? Now, if you find that you learn a lot by, you know, answering questions to check your knowledge and understanding, if you go to the main menu, click on Materials, click on the Start Here folder, and then click on the Resources folder, you will find a set of review questions for each chapter. You can work your way through those. That'll tell you what you know and what you don't know. I've always recommended that. And finally, if you think there's a likelihood of being asked about something that you really have had a tough time remembering, you know, like maybe you can't remember the steps to the scientific method or the sections of a lab report. Maybe you just can't remember them. Well, you are allowed to fill out a note card and take it with you to the final exam. Not a sheet of paper, not a notebook, a note card. So there are some things that we understand uh, need to be memorized, and perhaps you have found that difficult. Those kinds of memorization things you could jot down on your note card, have them available. Okay? So I always advise taking that note card. Then I ask after final exams, when I'm checking with the site coordinators and proctors, I ask them, you know, did anyone come in with a note card? Well, a couple did. It's just amazing how many don't. But you don't have to. You can go about this review and preparation and taking of the final exam any way you want. I'm only here to help. That's what I'm trying to do right now. As I've done the entire semester, I've tried to help you. As I've corrected your assignments, I have given you direction, hints, suggestions. Sometimes I've even flat out given you the right answer in case you wanted to redo that assignment for a better grade. And once again, I found that to be disappointing. Not too many took me up on that second attempt at assignments. Many of you tried slipping by tests and quizzes a third try. If you wonder whatever happened to one of your third attempts, I deleted it because it was made very clear to you you got 2 tries on everything, not 3. Okay, one last reminder. Before you check out of the course, I would like you to make sure that you do the knowledge inventory 2 so that I have a pre-test and post-test and can report progress to the State Department of Education, and to help IDLA in improving our methods, techniques, and the courses themselves, I would like you to do a course evaluation, which is found at the beginning of Unit 8. I will give you extra credit for submitting that. Now, the only thing I'm told is who took it, so I can dish out extra credit. Unfortunately, all responses, well, they're anonymous, so I have no idea what you said. So if you don't like me, you can pan me. I won't know. Okay? All right. If there's anything else you need as you finish up your makeup, as you prepare for your exam, yeah, contact me. You have my email. You have my toll-free phone number. Get a hold of me. I'm more than happy to help you. That's what I'm here for. So basically, this is our last study hall. So I'm not going to say until next time, so long, but uh, I will say a very fond farewell. For the most part, I've enjoyed this course and the students in it. I appreciate those of you who worked hard, followed instruction, and did your best. I ask nothing more. Thank you and goodbye.